Welcome to Precalculus Concept 29A. Underneath inverse trig functions, we're going to talk about inverse sine functions, and there's 3 boxes to cover. Alright, so let's recall what an inverse function actually is. So I have this graph on the left-hand side. I have in the orange equation y equals x plus 1 divided by 2. And the green equation, I have y equals 2x minus 1. And then I have the line y equals x. Okay, these are all linear, so they're just lines. So I'm doing this to illustrate the point that we know from a function, based on its graph, whether or not the function has an inverse, because it has to pass 2 things. It has to pass the vertical test, and it has to pass the horizontal line test. The graph of y equals x is the line in which the two functions themselves, the regular function and its inverse, are reflected about. So all of this is stuff that we have already covered and already talked about in class before. So the question then is, how does this apply to the new trig function, the sine curve that we have been working with? Okay, so I have graphed for you the y equals sine x, and as you can clearly see, it definitely passes the horizontal line test, meaning that there is no point that which the graph crosses more than once for any vertical line. So we're good to go there. The problem, of course, comes up when we try and invoke the horizontal line test. When I draw a horizontal line, I clearly see that there are a couple of places in which the sine function does not pass. So what are we supposed to do? We have to do something in order to even begin to talk about the inverse function, and that is what's in the next box. But I just wanted to recall your memory about how inverse functions work to begin with. So remember, if this is a point on my function, let's say this is the point 1/2 comma 0, then I am guaranteed the point 0 comma 1/2 will be on the inverse, 0 comma 1/2. So remember, you just flip the x and the y. Also remember that the domain and the ranges flip-flop in terms of inverses and functions. So that's all review, but there is something tricky going on here, and we have to talk about it in box number 2. Okay, here's box number 2. So as I spoke about in box 1, we know that we have a problem with the sine function because it simply does not pass the horizontal line test. Meaning if I draw a horizontal line, there are 2 places in which the graph crosses, so therefore this function doesn't have an inverse. So what we must do is we must restrict the domain. We must restrict the domain between negative pi over 2 and positive pi over 2. So notice that yellow horizontal line that I just drew for you on the x-axis. That is the same exact line over here. So I've just blown it up a little bit for you. And as you can see on the left-hand side, that I would only then be talking about this particular part of the graph. So if I include the points from negative pi over 2 to positive pi over 2, then you can see that all of these points pass the vertical line test, and they all pass the horizontal line test. So as long as we restrict our domain from negative pi over 2 all the way to positive pi over 2, then we can talk about an inverse function, and that leads me to this picture over here. So the black graph, again, is the graph of sine. I have the point negative pi over 2, negative 1, positive pi over 2, positive 1. The red line that you see here, of course, this is the line y equals x. So if I was to think about reflecting this black part of the sine curve over the line y equals x, the part that I would get is the blue curve. And the blue curve is the graph of the inverse sine function. And the way that we write it is the inverse sine of x. Notice that this point right here would just be the reverse of these 2 points. So instead of pi over 2, 1, I would have 1 comma pi over 2. So this is the value of 1, and this is the value of pi over 2. So 1 comma pi over 2. And this point would be negative 1 comma negative pi over 2. So the inverse sine function, to note, only lives in between quadrants number 4 and 1. What do I mean by that? This is quadrant number 4, and this is quadrant number 1. Because remember, if I was to go back over here and think about the sine curve in terms of quadrants, okay? In between here and here, this is quadrant number 1. In between here and here, this is quadrant number 2. Quadrant number 3, quadrant number 4, And then it would just repeat again, quadrant number 1. So if I backed up 1, this has to be quadrant number 4. Okay? So the inverse trig function only lives between quadrants 4 and 1. And we're going to practice with what we do with an inverse trig function in the next box. Okay, box number 3 are some examples of how we use inverse sine functions to solve problems. Here is a very, very basic, straightforward example. It says find the exact value. Okay, the way that you read this is as follows. Okay, when you see that, that means the angle whose sine is whatever this value is. Okay, so the sentence frame that I want you to think about is in this little box right here for each of these problems. So when you see this, I want you to say, in between quadrants 4 and 1, I am looking for the angle whose sine is rad 2 over 2. Okay, and here's the picture that goes along with that. So in between quadrant number 1 and quadrant number 4, this is where I can live. I can only live here. I know that sine is positive in quadrant 1. I know that sine is negative in quadrant number 4. So in between quadrants 4 and 1, I'm looking for the angle whose sine is rad 2 over 2. Well, that would be somewhere in quadrant 1, and I know that the sine of pi over 4 is worth a value of rad 2 over 2. So therefore, the inverse sine of rad 2 over 2 is pi over 4. That's what we're doing in all these problems, okay? So let's try part B. Okay? Part B says the angle whose sine is rad 3 over 2. So what we want to ask ourselves is, in between quadrants 4 and 1, I am looking for the angle whose sine is worth rad 3 over 2. So in between quadrants 4 and 1, I am looking for the sine, or the angle whose sine is rad 3 over 2. So I'm looking for this coordinate, rad 3 over 2. So where is the y value worth rad 3 over 2 in quadrant 1? Well, it would have to be at pi over 3 radians, okay? And if you don't know that, you can look back at your unit circle and see. So if I look back at my unit circle over here, I see here's pi over 3, and the sine value is worth rad 3 over 2, so therefore that must be the answer. So the inverse sine of rad 3 over 2 is equal to pi divided by 3, okay? Let's try this last one over here, part C. The inverse sine of negative rad 2 over 2. So what this means is the angle whose sine is worth negative rad 2 over 2. So the sentence frame that you read to yourself is, here's quadrant 1, here's quadrant number 4. So in between quadrants 4 and 1, I'm looking for the angle whose sine is worth negative rad 2 over 2. Negative rad 2 over 2. So that would be a value of negative pi over 4, because remember, you swing down to create that negative angle because you have to stay between quadrants 1 and quadrants 4. So the answer to this one would be negative pi over